to our study of integration, and this is the last section of Chapter 5 in our introduction to integration. This will be our last section before we finish up our quarter testing and start our reviewing for the semester exam. We'll do remember how we learned how to take derivatives, what a derivative was, and then we did applications of derivatives. We'll save the applications of integration, which are really cool problems. We'll save those for the beginning of the new year. Anyway, here's in order to find these antiderivatives, there is a ton of what I would refer to as integration techniques, a lot of them. In fact, when I took calculus, we spent a lot of time using trigonometric techniques, integration by parts and partial fractions, substitution. We spent a long time. Well, the first year course, there's only one technique you need to learn, and it's substitution. So, one thing to remind you, you know very few antiderivatives. Here they are. Here's how to integrate a constant times f of x. How to integrate a constant. You got sine, cosine, tangent. This one that's not one of the major ones. And here we got the inverse power rule. Not very many. We're going to apply one technique you need to learn in order to expand the amount of antiderivatives you can compute, and that is integration by substitution. Again, we know a lot of integration techniques come about from the fundamental theorem of calculus. For every derivative rule, there is typically a integration rule. So what's one of the derivative rules? It's the chain rule. Okay, so let's maybe we should write down what the chain rule was. Remember, the chain rule was the following: if I took the derivative of f of g of x dx, that would be what? Well, that would be f prime. Sorry, I'm putting integral symbols down. It's crazy. Okay, this would be the derivative of the outside function evaluated at the inside function times the derivative of the inside. We could put it in the front or the back. I'm going to put it in the back this time. Okay, so what I could basically say would be the following: if I would integrate then f prime of g of x, g prime of x dx, that could be, well, that could be f, the antiderivative of that would be f of g of x plus c, right? If I take the derivative of this, if I take the derivative of that, I get this back, right? So we're going to use that property, and it shows up all the time. Okay, how I'm going to set up the substitution case. I'm going on the left side of this. I've got kind of the general problem where you in general substitute, make a U substitution. On the right, I'm going to work a particular example, which is a little bit easier to see, I'm sure, than the general case. But I'll leave the general case up there for your notes. Okay, in order to work this, you got to get good at seeing. When you look at a problem, you've got to see the derivative here. And you see, when you're looking into substitution, you'll get good at seeing, oh, I see the derivative of that. And in particular, this particular called the integrand. This could be called the integrand. You don't know how to take the antiderivative of it, but you know how to take the antiderivative of f prime. You know what f is, okay? But you got to see the derivative. Here I'm looking at this particular, and I notice that x is a form of the derivative of g. Okay, notice there could always be a constant out here too. Could always be a constant. Here I see the derivative is x. So I'm going to set u, and now I'll go back to a different, not such an obnoxious color. I'll let u equal to 4x squared minus 1, because I know the derivative of this is going to give me a function of x. Then I take the derivative. I say, well, what's du dx? This is going to be equal to 8x. I multiply now both sides by dx, which I can do that. It's just a, this is a ratio, right? It's the change in y, which in this case is u, over the change in x. These are going to cancel, and I'm going to get du is equal to 8x dx. Now I want to match something. The next thing I'm going to do down here, I want to match k g prime to this j. I want to get this knockout, what I call the knockout blow right here. I want that function. So I say, I divide both sides by 8 in order to 8x dx over 8. That's going to be equal to what? X dx. And that, my friend, I refer to as the knockout right here. You see, I see that substitution. Now I'm going to substitute back into the original equation. Well, what do I have here? I have u to the, I got the square root of u. What's x? That's du over 8. Or that's just going to be 1/8 u du. Oh, sorry. Square root of u. Remember, when I want to take that derivative, the first thing I want to do is rewrite this as u to the 1/2 du. Okay, so now this ought to be an integral on my table. Remember, there's not many antiderivatives that I know, but I do know this one. So I've taken a problem where I don't know what the antiderivative is here, right? I do not know that. I see the derivative. I notice the derivative comes from the other part of the integrand. I make a u substitution, and now I've got a new antiderivative find that's much more manageable. Okay, let's continue to finish this problem. You see, I'm just writing down what I did before. I'm on step 4. Now step 5 says find the antiderivative. Okay, we got an easy part now. Now comes the easy part. It's 1/8. Oops. It's going to be 1/8. And I use the power rule here, right? U to the 3/2 over 3/2. Or that might be thought to be 2. I'm going to flip the be 2/3 or 2/24 u to the 3/2. Better put my constant of integration here too, right? Oops. Plus c. So this is going to be equal to 1/12 u to the 3/2 plus c. Now, notice when I started this problem, I find the antiderivative of the easier problem. Yes, I just did that. This is the easier problem, but now what's the next thing I want to do? I want to substitute u back into the original. Okay? I want to get this back, and so what was u equal to? Well, u is equal to 4x squared plus 1 here, so I get the answer is 1/12 4x squared plus 1 to the 3/2 power plus c. That, I believe, should be my answer. Now, if I have time, though, I can always check it, right? Differentiate the result to check answer. If I differentiate, I take the derivative of this antiderivative right here. I better get back to this. I better get back to that, right? That's what an antiderivative is. Well, let's see if that happens. Okay, we used the chain rule on this. I'm going to, what's the derivative of the inside? Well, that's just 8x. 8x, okay, I'll keep the 12 out front. Now I'm going to power this thing down. I get 3 halves, 4x squared plus 1 to the 1 half, plus what's the derivative of a constant? That's 0. Okay, let's clean this guy up a little bit. This looks like it's 24 over 24 x. I'll rewrite this as 4x squared plus 1. That goes to 1, so it's x times 4x squared plus 1. And check, x times 4x squared plus 1. That is our original problem. Okay, so we have found the correct antiderivative. We've done integration by substitution. And that's what we need to do. We just need to work a bunch of problems. Remember how this starts. I need to see the derivative. Let me work one more problem, and perhaps that'll show you what I mean. Here's another classic problem. I'm going to do sine of x times the cosine to the 4th power of x dx. All right. Now, you look at this problem and you'll think it looks darn near impossible, but you'll start to realize this is a piece of cake. Now, you need to use substitution. You need to see a derivative. Well, maybe it's worth to do it the wrong way and the right way. Let's do it the wrong way. There's only 2 substitutions I can make, and we'll change pens to blue. I could set u equal to, let's try the sine of x. Because I see, wait a minute, well, there's a derivative, cosine of x. Oh, but it's to the 4th power. That could be a problem. Let's see what we got here. Well, du dx is equal to the cosine of x. Du is equal to the cosine of x dx. Okay, let's substitute back in. We're going to get what? Well, we're going to get sine. Sine is just u. Okay, cosine, well, we got a du, but then we still got a cosine cubed of x. That's, what do I do now? I got x's and u's. That's just wrong, okay? Wrong approach. When I say I see a derivative, what I really see here, I see the derivative of a cosine is a sine, or the negative sign. So I'm going to say u is equal to the cosine of x. Du dx, which we'll stop doing that pretty soon, but that's minus sine of x. So I'll skip the step of multiplying through, but du is minus sine of x dx. And now I'm going to say a negative du is equal to the sine of x. This is the way I do it. Again, what do I call it? Yep, that's right, the knockout. Sine of x dx. Got it. Sine of x dx is minus du. Now I rewrite that integral now as what? Well, it's just u to the 4th power times negative du, which is the same thing as saying negative u to the 4th power du. And see, now we've got an integrand which we know the antiderivative of. What's that going to be? Well, it's just going to be negative u to the 5th over 5 plus c. Well, what's u? We substitute back in. U is equal to the cosine, so the answer is minus 1/5 the cosine of x to the 5th power plus c. This would be our antiderivative. Okay, we'll work a lot of these problems, spend 2 days on this, but you got to get good at this technique, and then you'll be able to find many antiderivatives. See you soon.